In this video, we'll focus on how to write clean, maintainable, and reusable code using functions in Python. Functions are an essential tool for managing complexity as your programs grow in size. Instead of copying and pasting code or writing large monolithic scripts, functions allow you to divide a program into logical building blocks, each one handling a specific task. By isolating behavior, you can test individual parts of your program more easily, make updates with less risk, and create code that's easier for others to understand and maintain. This presentation will introduce the syntax and structure of functions, demonstrate how to define and call them, and explore Python-specific features that make functions especially powerful. Building Python Programs with Functions by the Programming Professor. Here's an outline of the topics we'll cover in this presentation. We'll begin with the basics of defining and calling functions, including syntax and naming conventions. Next, we'll explore how to design and build functions incrementally, and how to work with different kinds of arguments, including default, keyword, and variable length arguments. We'll also look at how to return multiple values from a function using tuples. Then we'll dig into scope and namespaces, which govern how variables behave inside and outside of functions. Along the way, we'll explain how Python treats functions as objects, which allows them to be assigned to variables or passed as arguments. We'll wrap up by covering common function-related errors and best practices for writing documentation using Docstrings. This module is foundational for writing modular and professional-grade Python code. Programs often involve repeated logic or similar operations performed in multiple places. Writing out the same code over and over not only makes your programs longer, it also increases the chance of introducing inconsistencies and errors. Functions solve this problem by allowing you to group related operations into a reusable block of code. But even when code isn't repeated, functions still serve a valuable purpose. They help organize your program into meaningful sections that are easier to test, reason about, and maintain over time. When used effectively, functions improve readability and promote cleaner design. This makes it easier for both you and others to understand the purpose of each part of your codebase. At the most basic level, a function in Python is a named block of code. You define a function using the def keyword, followed by the function name and parentheses. Inside the function, you write one or more indented lines of code that will run when the function is called. To actually use the function, you call it by name, with parentheses optionally passing in any required arguments. Once the function finishes executing, control returns to the line that originally called it. Python also comes with many built-in functions, like input, int, and len, but user-defined functions let you add your own custom behavior. It's good practice to use lowercase letters and underscores in function names, such as getName or calcaria. This helps make your code more readable and consistent. Functions don't just run code, they can also return results. A return statement allows a function to produce a value and send it back to the place where the function was called. For example, a function might calculate a square and return the result using return x times x. A function can return only one value directly, but if you need to return multiple pieces of data, you can package them in a list or tuple. If a function has no return statement, or if you use just return with no value, the function returns none by default. Python also allows multiple return statements in the same function, letting you exit early based on conditions. This ability to return values makes functions extremely powerful, allowing them to behave like building blocks in larger expressions or data processing pipelines. Functions become even more powerful when you customize their behavior using parameters and arguments. A parameter is a variable listed in a function's definition. It's a placeholder for input that the function will receive. When you call the function, you provide actual values called arguments, which are matched to the parameters. For example, in the function calcPizzaria, diameter is the parameter, and 12.0 might be the argument you pass during the call. Inside the function, the parameter behaves like a local variable, and once the function returns, the parameter is no longer accessible. You can also pass in expressions as arguments, such as x times 1.5, which are evaluated before the function is called. Understanding how parameters and arguments interact is key to writing flexible, reusable code that responds dynamically to different inputs. Functions in Python can accept multiple parameters or none at all. When defining multiple parameters, you simply separate them with commas, as in def add x, y. During the function call, arguments are matched to parameters by position, so the first argument goes to the first parameter, the second to the second, and so on. It's also possible to define functions that take no parameters at all. These are still called using empty parentheses, like say hello. Parentheses are required for every function call in Python, regardless of whether any input is needed. These rules help maintain consistency and predictability in how functions behave. Whether your function needs detailed input or is just performing a standard operation, Python's function syntax makes it clear what's expected. A function in Python can even call another function as part of its own logic. This is known as a hierarchical function call or nested call. For example, this statement contains two function calls. Input runs first and collects a string from the user, and then int immediately converts that string into an integer. These nested calls are evaluated from the inside out. Using hierarchical calls like this helps streamline your code by reducing the need for intermediate variables. Instead of writing separate lines to capture and convert input, you can nest the logic into a single expression. This not only makes your code shorter, it often makes it easier to read and reason about, especially when the operation is logically one cohesive step. Another common use case for functions is to encapsulate printing logic, especially when the same output needs to appear in multiple places. When you place print statements inside a function, you keep the main part of your program clean and focused on logic rather than presentation. Functions that print things don't usually need to return a value, so they're often referred to as void functions. They return none by default. These are useful for performing side effects like showing menus, status messages, or formatted data. Separating printing into its own function improves structure and reusability. You can reuse the same message or layout in multiple parts of the program without duplicating code, and you can update formatting in one place without touching the main logic. When you encapsulate output in a function, you gain the ability to reuse it anywhere in your code, whether that's in a loop, in response to user input, or as part of a larger output sequence. This not only prevents repetitive code, but it also makes your program easier to maintain. If you need to change the wording or formatting of your print statements, you only have to do it in one place. This practice also helps enforce consistency. Menus, error messages, and summaries will look the same no matter where they appear in the program. It's a clear application of the dry principle. Don't repeat yourself. Small, single-purpose print functions are an easy way to improve the organization of your code while making updates less error-prone. This is an example of using functions to build a simple menu system. The function print menu encapsulates all the output needed to display the menu options: Gumbo, Jambalaya, or Quit. This function is then reused within a loop that continues prompting the user for a choice until they select option 3. By encapsulating the menu output, The program avoids repeating the same print statements each time, and it keeps the loop logic clean and focused. The example also demonstrates conditional branching within the loop to handle different menu choices. This pattern, using a print function for display and a loop for interaction, is a solid foundation for building larger command line interfaces. It's easy to update, and because the print logic is separated from control flow, it's also more readable and maintainable. Python functions are dynamically typed, which means they can accept arguments of any data type. For example, the same function add might return 12 when passed two integers, or return the concatenated string torabora when passed two strings. This behavior is known as polymorphism, where the same function behaves differently depending on the type of its input. Python's built-in operators exhibit the same kind of polymorphic behavior. For instance, multiplying a string by an integer results in repeated strings, while multiplying two integers gives a product. This dynamic behavior makes Python functions flexible and expressive, but it also requires you to be mindful of what types your functions are receiving and returning. Well-documented expectations, or type annotations, can help avoid errors when working with dynamically typed arguments. Python's use of dynamic typing allows a variable to hold values of any type and even change types during program execution. For example, a variable named num could be assigned an integer at one point and then reassigned to a string later. Unlike statically typed languages like C++ or Java, where you must declare variable types explicitly, Python determines types at runtime. This makes Python more flexible and easier to work with for rapid development. However, it also introduces the possibility of type-related errors that only show up when the program runs. These errors can be subtle and hard to catch without careful testing. While dynamic typing makes Python more concise and beginner-friendly, understanding its behavior is essential for writing robust, bug-free code, especially as your programs grow more complex. A related concept is duck typing, which is a key feature of Python's dynamic type system. The phrase, "if it walks like a duck and quacks like a duck, then it's a duck," captures the idea well. In Python, you don't ask whether an object is a string, you simply check whether it behaves like one. If an object supports string-like behaviors such as slicing, indexing, or case conversion, Python treats it as a string without requiring it to formally inherit from a string class. Duck typing prioritizes behavior over explicit type declarations. This allows your functions to work with a broader range of objects, as long as those objects provide the expected methods or behaviors. While duck typing increases flexibility and reusability, it also places greater responsibility on the programmer to understand how the objects being passed into functions will behave. As programs become larger, they can also become harder to read and manage. One of the most effective solutions to this problem is to use functions to decompose the program into smaller, understandable pieces. Each function should represent a clear and focused task. This structure improves readability, makes the code easier to test, and reduces the mental load on the programmer. Even short programs benefit from being broken down into well-named, single-purpose functions. Doing so not only helps you debug issues more easily, but it also sets up your code to scale better when new features or modifications are needed. Function-based decomposition is one of the cornerstones of clean code design and is essential for effective collaboration in team-based development environments. Functions support modular development, which means breaking a large program into manageable, self-contained components. This approach allows you to write and test each part of your program independently before integrating them into a complete solution. Think of it like building a complex project out of clearly labeled building blocks. To get started, you can define function stubs, simple placeholders that outline what each function should do. Even if they aren't fully implemented yet, stubs help you plan and structure your program effectively. This process is similar to sketching out a road trip before you start driving. You map the route first, then fill in the details. This mindset not only leads to cleaner and more scalable code, but it also helps you and others more easily understand how your program is organized and what each part is responsible for. One of the most important reasons to use functions is to avoid redundant code. Repeating logic across your program not only clutters the code base, it increases the risk of errors and makes updates more difficult. Instead, define a function once and reuse it wherever needed. For example, rather than rewriting the math for calculating square roots every time, you can call Python's built-in math.sqrt function. Each function should have a single, well-defined purpose, and the main program should read like a high-level summary of those steps. A good rule of thumb is to keep each function under about 30 lines, though clarity is more important than strict length. By encapsulating logic in reusable, consistent units, you simplify maintenance, improve reliability, and make your code easier to extend. Mathematical functions are a classic use case for defining reusable logic. These functions accept one or more numeric inputs, perform a calculation using a formula, and return the result to the caller. For example, a function could convert a person's height from feet and inches into centimeters by applying a specific formula. Rather than writing out that formula every time you need it, you encapsulate it in a function like convert to cm. This makes the logic reusable and easier to modify if the formula ever changes. Mathematical functions are especially helpful when the same calculation appears in multiple places, or when it's part of a larger expression. They promote accuracy, reduce duplication, and keep your main program focused on higher-level logic instead of the low-level math. Function calls can be used inside expressions, allowing for compact, readable code. When a function returns a value, that result can be used just like any other value in Python. For example, you could write 5 plus compute square of 4, and Python will evaluate the function call first, substitute its result, and then compute the final sum. This behavior allows you to nest function calls or include them in arithmetic expressions, string formatting, or conditional statements. The key requirement is that the function must return a usable value. Functions that return none, like print functions, can't be embedded in expressions this way. By using return values effectively, you can create expressive and efficient code that reads clearly and executes in fewer lines. Complex mathematical operations are often easier to manage when broken into multiple helper functions. This modular design approach lets you isolate individual pieces of logic, such as computing the area of a circle's base or calculating the surface area of a cylinder. For example, a base area of radius function might return the area of the circular base, and that result can be reused in both a volume function and a surface area function. This makes your code more reusable, easier to test, and less prone to bugs. Instead of embedding long formulas directly into your main program, you build a toolbox of smaller, focused functions that you can compose to solve more complex problems. This approach not only improves clarity, but also supports better maintenance and long-term scalability. Large programs are often written using an incremental development strategy, where code is written and tested one piece at a time. This is especially helpful when working with functions. You start by writing function stubs, which are placeholders for functions you plan to implement later. These stubs let you build the structure of your program without getting bogged down in details right away. It's a way of saying, this function will exist here eventually. The benefit is that you can test the flow of your program before all parts are fully functional. Stubs encourage modular thinking and help, prevent you from writing large blocks of untested code. While a stub doesn't perform any real work yet, it plays an essential role in building and refining your program gradually and thoughtfully. In Python, you can create a stub using the pass keyword. This lets the function exist syntactically, but do nothing. For example, you might define steps to calories with pass inside the body, while you work on another function like steps to feet. When you call the incomplete function, Python simply skips over it. In the meantime, the rest of your program can run without crashing. The output might show none for now, but that's expected. Pass functions return none by default. This placeholder approach is especially useful during prototyping or when you're collaborating with others and want to outline interfaces without filling in all the logic just yet. It allows you to build one part at a time without needing everything to be fully wired together. Instead of using pass, you can make stubs more informative by printing a message and returning a placeholder value like -1. This is helpful when you want a visual reminder that a function hasn't been completed yet. For example, you might print fix me, finish steps to calories, and return -1 so the output clearly signals that something is missing. This strategy prevents confusion during testing and helps avoid silent errors. A placeholder return value makes it obvious that your logic still needs attention, while allowing the program to remain functional. It's a small change that improves clarity and makes development smoother, especially in larger programs where incomplete functions could be accidentally overlooked. In some cases, you may want your program to stop entirely if an unfinished function is called. Python allows this using raise not implemented error. This statement throws an exception as soon as the stub function is executed, clearly indicating that this part of the program should not run until it's implemented. This is especially useful for core functions, those that are essential for correct program behavior. If you're building a project with collaborators or managing a large code base, this approach prevents others or yourself from accidentally using incomplete logic. It also serves as a clear signal during testing. If a not implemented error is raised, it means you've reached a planned point of development that still needs work before proceeding. This is an example of a program that raises not implemented error when a stub function is called. In this case, getPoints is a placeholder function that's supposed to collect coordinate data from the user. But since it hasn't been implemented yet, the function raises an exception immediately. This prevents the rest of the program, which calculates the perimeter of a triangle, from running. Notice that the other functions, like sideLength and getPerimeterLength, are complete and ready to work. By raising an error in getPoints, the program ensures that all required input logic is in place before proceeding with dependent calculations. This pattern is effective for enforcing development discipline and catching missing functionality during early testing. This practical example combines multiple function concepts in one real-world application, calculating eBay listing fees. The function calc eBay fee calculates the total fee based on tiered percentage rates. It uses conditional logic to apply different rates depending on the selling price: 13% for the first $50, 5% for amounts up to $1,000, and 2% beyond that. Inside the function, branching and mathematics are combined to return the final fee. The function is then called with user input, and the result is printed. This example illustrates how return values, conditional statements, and mathematics can be integrated inside a function to model real-world pricing systems. It's a great reminder that functions aren't just for math problems. They're essential tools for building reusable, context-specific logic in software systems like web apps, e-commerce platforms, and financial tools. In Python, functions are objects, just like strings, integers, or lists. That means they have a type, function, an identity, memory address, and a value. When you write a function using def, you're actually creating an object that can be stored, passed around, or manipulated like any other variable. For example, defining def printface creates a function object, and the name printface refers to it. This object can be assigned to other variables, passed into other functions, or even stored in data structures like lists or dictionaries. Recognizing that functions are objects opens up more advanced programming techniques, such as higher-order functions, decorators, and callbacks. Python compiles code into bytecode before executing it. This process happens automatically when a function is defined, when a module is imported, or when you enter code in the interpreter. When you call a function, like printface, Python transfers control to that function's compiled bytecode and executes it. Because functions are objects, you can assign them to variables or pass them as arguments to other functions. This makes Python extremely flexible and expressive. You're not limited to just calling functions in the traditional sense. You can build new kinds of control flow or abstraction by treating functions as data. Understanding this compiled nature of functions also helps clarify how Python runs your code behind the scenes. Here we see an example that demonstrates how functions can be assigned to other names and called through those aliases. First, the function printface is defined to print a simple facial expression. Then, it's called in the usual way. After that, the same function is assigned to a new variable, func. When func is called, it executes exactly the same code. What's happening is that both printface and func point to the same function object in memory. This concept is important when you start working with callbacks, function dispatching, or functional programming patterns. Being able to store and reuse functions in this way adds an extra layer of modularity and flexibility to your programs, and it's part of what makes Python such a versatile language. Here we will explore how passing functions as parameters can simplify and clean up your code. Without function parameters, you might need to use conditionals or repeated calls to different functions. But by passing a function into another function, like printFigure with the parameter face, you can choose which specific behavior to execute without rewriting logic. This allows your program to stay flexible and scalable. For example, if you have several different ways to print a figure's head or body, you can define each piece as a function and decide at runtime which one to use. This technique reduces duplication, improves clarity, and makes your codebase easier to maintain. Treating functions as first-class objects, able to be passed, returned, and stored, is a hallmark of Python's design and a powerful tool in more advanced programming workflows. A common source of bugs when working with functions involves copy-paste errors. Reusing existing code is a standard practice, but it requires careful attention when making modifications. In the example shown, two functions are defined, one to convert Celsius to Fahrenheit and another to convert Fahrenheit to Celsius. The mistake happens when the second function is duplicated from the first, but the return statement is not updated correctly. Instead of returning the final Celsius value, it mistakenly returns the original Fahrenheit input. Errors like this don't always produce immediate runtime issues, but they cause incorrect results and hard-to-find logic bugs. It's a reminder that even small oversights, like not updating a return variable, can impact program correctness. Always double-check return statements when duplicating code, and consider writing unit tests to catch these subtle mistakes early. Functions can also behave incorrectly if you return the wrong value or forget to return anything at all. For example, a function that computes temperature but accidentally returns the input instead of the result will produce unexpected behavior. Worse yet, if a function forgets to include a return statement entirely, Python will return none by default. This silent failure can go unnoticed until the result is used in a calculation or printed in the output. It's especially problematic in larger code bases, where a function's return value may travel across multiple layers of logic. The takeaway here is to always review the return paths in your functions. Make sure each function returns exactly what it's supposed to, and don't assume that assigning a value to a variable means it will be returned. One kind of logic error is one that results when a return statement is omitted. In the example, the function stepsdefeat calculates a number based on input, but it never explicitly returns that value. As a result, when the function is called, the variable assigned to hold the result actually gets none. This is a perfect example of a function that looks complete and even runs without a syntax error, but produces incorrect output. These kinds of bugs are especially hard to detect because there's no immediate crash or traceback. That's why it's crucial to always confirm that your functions return the value they're meant to. This becomes even more important when writing code with side effects, conditional logic, or multiple return paths. When in doubt, add print statements or use assertions to verify that returned values are what you expect. In Python, scope determines where variables can be accessed or modified. This slide focuses on local scope, which refers to variables defined inside a function. These local variables exist only within that function. They're created when the function is called and destroyed when the function exits. For instance, in the inches to cm function, variables like total inches and centimeters are not accessible outside the function. This behavior helps prevent unintended interactions between different parts of your code and makes each function more self-contained. Local scope is essential for maintaining modularity and avoiding naming conflicts. When writing functions, always assume that their internal variables are private unless you return them explicitly. Understanding local scope also sets the stage for learning about global scope, closures, and more advanced concepts in function design. Global variables are defined outside of all functions and have a broader scope, extending from their point of definition to the end of the file. Inside a function, you can read a global variable without any special syntax. But if you want to modify a global variable from within a function, you must use the global keyword. Without it, any assignment creates a new local variable, even if a global with the same name already exists. This can lead to confusing bugs where a change you thought was global is actually confined to a function. The slide demonstrates this with an example. Employee name appears global, but is shadowed by a local variable unless the global statement is used. While global variables can be convenient, they should be used sparingly and carefully, especially in larger programs. Overusing them can make code harder to debug, test, and reason about. Here are some guidelines for working with global variables in Python. While global variables can be accessed throughout a program, modifying them inside functions can introduce serious risks. If a function changes a global variable using the global keyword, it creates a side effect, an external change that's often hard to trace or predict. This can make debugging and testing much more difficult, especially when multiple functions interact with the same global state. The slide emphasizes a best practice. Reserve global variables primarily for defining constants, not for storing mutable program state. If you do need to share data between functions, consider returning values or using parameters instead. By limiting the use of global assignments, your functions remain more modular, more testable, and easier to reason about. Function scope and definition order also affect program behavior. A function must be defined before it's called. This means that Python won't recognize a function name until it has parsed the def block and created the function object. If you attempt to call a function before its definition appears in the script, you'll get a name error. This is particularly important when your program is organized into multiple functions that call each other. The solution is to structure your file so that all function definitions come before any code that uses them. Alternatively, move your logic into a main function and call it after all definitions. This rule reinforces the idea that function scope begins only after the function is defined, and that Python interprets code from top to bottom. Namespaces are how Python keeps track of names and their associated values. Every time you assign a variable or define a function, Python adds an entry to a namespace, a kind of internal dictionary that maps names to objects. For example, when evaluating z equals x plus y, Python looks up the values of x and y in the current namespace, computes the result, and assigns it to z. There are different namespaces in a Python program: local, global, and built-in. You can inspect them using functions like globals and locals, which return dictionaries of currently defined names. Understanding namespaces helps you debug scope issues and reason about how your code is executed. It also lays the foundation for more advanced topics like closures, decorators, and object-oriented design. Python follows a specific scope resolution order when it encounters a variable name. First, it looks in the local scope, which includes variables defined within the current function. If it doesn't find the name there, it moves to the global scope, which includes variables defined at the top level of the file. Finally, it checks the built-in scope, which includes standard functions like len or print. If the name isn't found in any of these places, Python raises a name error. Understanding this hierarchy is essential when you're debugging variable errors or shadowing issues. It's also useful when you're designing functions. Knowing where and how a variable is resolved can help you avoid accidental overrides or misinterpretations of scope. When a function is called, Python creates a new local namespace for that function. Any parameters or variables created during the function's execution exist in this temporary space. This slide demonstrates how Python resolves names across local and global scopes. If a name is not found locally, Python will look to the global namespace next. In the example shown, calsLeft is a parameter defined locally in the function, while sodacals is defined globally. Python resolves both successfully by checking in the correct order. This structure ensures that functions don't accidentally interfere with each other's variables, while still allowing controlled access to global values when necessary. Each time the function runs, its local namespace is rebuilt from scratch, ensuring that function calls remain isolated and predictable. Multiple variables with the same name can exist in different scopes without interfering with each other. In the example, there's a global variable called tmp, and a separate local variable also named tmp inside the avg function. When avg is called, Python uses the local tmp for its calculations, and after the function finishes, the global tmp remains unchanged. This is possible because each scope, local, global, and built-in, maintains its own namespace. By default, assignments inside a function create local variables, unless you explicitly declare them as global. This behavior is useful for isolating function logic and avoiding side effects. But it also means that if you're not careful, you might accidentally shadow a global variable with a local one of the same name, leading to confusing or incorrect behavior. Always be aware of where and how your variables are defined. In Python, arguments are passed by object reference, which is sometimes described as pass by assignment. When you call a function, Python creates a new local variable that refers to the same object passed in. This means that the local parameter and the original argument share the same object, at least at first. If the object is mutable, such as a list or dictionary, changes made inside the function will affect the original outside the function. But if the object is immutable, like a string or an integer, the behavior is different. Any operation that seems to change the value actually creates a new object in memory. Understanding this difference is essential for predicting whether a function call will produce side effects or leave data unchanged. Whether or not a function modifies its input depends on the mutability of the object being passed in. Python distinguishes between mutable and immutable objects. Immutable objects, such as integers, strings, and floats, cannot be changed in place. When you modify them, Python creates a new object in memory, and the original remains untouched. In contrast, mutable objects like lists, dictionaries, and sets can be changed in place. So if you pass a list into a function and modify it inside, those changes will be reflected outside the function as well. This is why it's important to know the type of object you're working with. If you want to avoid unintended side effects, especially with mutable types, consider making copies before passing them into functions. As functions become more complex, they may require many arguments, which can make function calls harder to read and maintain. Consider a function like printBookDescription that requires 7 different parameters: title, author, publisher, year, version, number of chapters, and number of pages. Calling such a function with all positional arguments becomes difficult to manage and easy to get wrong. It's hard to tell which argument corresponds to which parameter without looking at the function definition. This reduces readability and increases the likelihood of introducing bugs. The solution: use keyword arguments, which allow you to specify parameter names explicitly, making your code more self-documenting and less error-prone. Keyword arguments make function calls clearer and more reliable. Instead of relying on the order of positional arguments, you can specify values by name, such as title equals The Lord of the Rings and year equals 1954. This not only improves readability, but also helps prevent mistakes like mixing up argument order. Keyword arguments are particularly helpful when a function has 4 or more parameters, or when some of the values are optional. They also make your code more flexible, since you can pass arguments in any order as long as you use their names. One important rule to remember is that positional arguments must come first, followed by any keyword arguments. Adopting keyword arguments in your function calls is a best practice that leads to clearer, more maintainable code, especially in larger or team-based projects. Functions in Python can also have default parameter values, which allow some arguments to be optional. This means that when calling the function, you can omit those arguments if you're okay with using the default values defined in the function header. For example, in printDate, with the parameters day, month, year, style equals 0, the style parameter defaults to 0 if not specified. This makes the function more flexible. You can call it with or without the optional parameter depending on the use case. In the example, different formatting styles for dates are selected based on the value of style. One key detail to remember is that only trailing parameters can have default values. You can't place a default parameter before a required one unless you're using keyword arguments explicitly. Default parameters are especially useful when you want to provide common behavior while still allowing customization when needed. While default parameters are convenient, they come with some pitfalls to watch out for. First, if you forget to pass a required argument and no default is provided, Python will raise a type error. More subtly, using mutable default values like lists or dictionaries can lead to unexpected behavior. For instance, if you set a default like myList, the same list object is reused across multiple function calls. This can cause the list to accumulate changes from previous calls, even when you expect it to be empty each time. The recommended pattern is to use none as the default value, and then create a new list inside the function if needed. This ensures a fresh list is used every time the function runs. Being aware of these subtle issues is part of writing robust, predictable Python code. Sometimes you'll want a function to accept a variable number of arguments, and Python supports this using single asterisk args and double asterisk quargs. The single asterisk arg syntax gathers extra positional arguments into a tuple, allowing the function to handle any number of unnamed inputs. Similarly, double asterisk quargs collects keyword arguments into a dictionary, which is useful when you don't know in advance which named parameters might be passed. These patterns are especially powerful in utility functions, logging systems, or wrappers where flexibility is key. While args and quargs are conventional names, they can technically be named anything, like single asterisk items or double asterisk options. These tools allow for greater generalization and help you build functions that scale more easily across different use cases. When using single asterisk args and double asterisk quargs, syntax rules and ordering matter. All regular positional parameters must come before single asterisk args, and double asterisk quargs must always come last in the function definition. This order, positional parameters, then single asterisk args, then double asterisk quargs, ensures Python knows how to assign incoming arguments correctly. For example, in def make sandwich main, asterisk condiments, double asterisk extras, the main ingredient is required. Condiments can include any number of additional toppings, and extras might include named options like size or packaging preferences. Understanding this structure is essential when designing flexible APIs or utility functions. It gives you the ability to handle both structured and unstructured input cleanly and predictably, and it reinforces the importance of designing function interfaces that are both powerful and intuitive. Sometimes a function needs to return more than one result, but Python functions can only return a single object. The solution is to package multiple outputs into a container, most commonly a tuple or a list. Tuples are ideal when returning a fixed number of related values. For example, a function that calculates both the mean and standard deviation of a dataset. The caller can then unpack the results into separate variables in a single line. This technique helps preserve clarity while still providing flexibility. Instead of writing multiple functions or returning a complex object, you can return a tuple of related results and let the caller handle them as needed. This approach is common in data processing, statistical analysis, and anywhere intermediate results are needed for further computation. This is a practical example of returning multiple outputs from a function using a tuple. The function getGradeStats takes a list of student scores and calculates both the average and the standard deviation. After performing the calculations, it returns the two results as a tuple. Back in the main program, that tuple is unpacked into two separate variables, average and standard deviation, which are then printed. This pattern is widely used in Python. Instead of returning a complex object or using global variables, you return a single tuple containing the results you need. It keeps the function focused and avoids side effects. This example also highlights Python's ability to work elegantly with simple data structures for multi-value outputs, ideal for analytical tasks, report generation, and clean function design. Unpacking a tuple into separate variables is a clean and intuitive way to handle multiple return values from a function. When you return a tuple, Python allows you to assign each element of the tuple to its own variable in a single line. This improves readability and makes the flow of data clear. It also makes your code less error-prone by avoiding the need to access values by index. The slide also reminds us that parentheses around a return tuple are optional. While lists could also be used, tuples are preferred when the number and meaning of returned values are fixed. This approach is a great example of Python's simplicity and expressiveness when designing function interfaces. Documentation is an important part of writing reusable and maintainable code. And in Python, the standard way to document functions is through docstrings. A docstring is a string literal placed at the very start of a function's body, enclosed in triple quotes. It should clearly describe what the function does, and if the function is more complex, it should also describe its arguments and return values. For simple functions, a one-line docstring is usually enough. For more complex ones, a multi-line docstring that includes argument types, optional values, and expected behavior is best. Good docstrings make your code easier to use and understand, not only for other people, but also for yourself, especially when revisiting older code. They also allow you to use the built-in help function to view documentation directly from the Python interpreter. These examples demonstrate how to write good docstrings. The first example demonstrates a one-line docstring, which is appropriate for short, simple functions. The second example is a multi-line docstring that describes the purpose of the function, the types of arguments it accepts, and optional keyword arguments. This level of detail is helpful for both human readers and tools that automatically generate documentation. The use of triple quotes and consistent formatting is important. Docstrings should not be preceded or followed by blank lines inside the function body. If you write clear docstrings from the start, your code will be more approachable and easier to debug, extend, or reuse. And when you or someone else uses help function name, the docstring becomes instantly available, which is a great feature for interactive programming and collaboration. Finally, we will summarize the key concepts about functions covered throughout the presentation. Functions allow you to group code into named, reusable blocks, making your programs more organized and easier to maintain. You've seen how Python supports flexible calling patterns using positional arguments, keyword arguments, and default values. We discussed how scope affects variable visibility, how functions can return multiple values, and how functions themselves are first-class objects that can be passed around like data. Finally, we emphasized the importance of clear function design and documentation using docstrings. Mastering these concepts gives you the tools to write modular, scalable, and high-quality Python code. Whether you're working on small scripts or building full applications, effective use of functions is a foundational skill in programming. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.